What's up, guys? Today we'll code something really exciting. We're gonna be creating a tool called Toralizer. It's a command line client for connecting to the Tor privacy network. When you run a CLI command for doing a network call, for example curl, the following thing happens. The connect function is invoked and the program establishes a TCP connection to the remote server, and then the communication begins. But with this tool, you'll be able to put the word Toralize in front of any command which does a network call. Toralize will intercept any calls to the connect function and execute our function instead. The traffic will be redirected to a local proxy server, which is a part of the Tor software. It will connect to the Tor network and then to the destination server, effectively masking your identity and helping you to stay private on the internet. And the best thing is, coding this is easier than you might think. Let's get on with it. Okay guys, welcome to this episode. The first thing we need to do today is we're gonna create our own proxy server client. So this proxies, it uses a protocol named SOCKS, S-O-C-K-S. And there are two different protocol versions, version 4 and version 5. And the Tor network and the software supports both these versions. Version 5 is a little bit more complicated, but version 4 should be very easy to implement. And it will be perfect to do it in C. So that's the task of today, creating our own client for that SOCKS proxy and use it to connect to the Tor network. So how do we start? I'm gonna start by logging into my CodePlanet server like this and prepare my screen as I usually do. Today I'm not gonna be coding in Nano or VI like I usually do. This is a little bigger project, a little bit more ambitious. Could do it in VI, even though it's a big project, but I'm gonna be using VS Code today actually. I'm gonna do my while true command so I don't accidentally close down my screen window like this. And since I am using a remote server, I need to somehow either upload my C files and stuff to that server or code remotely in VS Code somehow. And I'm gonna be using a tool which is called the Sociopath SCP client. Like this. If you want to download Sociopath SCP client. It's a tool that uses the SCP protocol, which is basically installed on every server, to upload and download files and subdirectories. And there's also a remote file editing feature that we're going to use today. Okay, so let's begin there. I have started up the program, which looks like this. So I connect to my CodePlanet server and I go to my code folder. So on the left side is my local hard disk drive, and on the right is the files and directories on the server. So I'm gonna right click and create a new directory, which I'm gonna call Toralize, this. And now I'm gonna select the Toralize, I'm gonna right click and I'm gonna click open in editor. Then it's gonna download everything in that folder, which is currently empty, but if it were any code files in that folder, it would download it to temporary directory and open it in VS Code. And each time you save or create a file or a directory inside of VS Code, it automatically updates on the server. Okay, so now I have this emptied here. So I right click and create a new file, which I will be calling Toralizer.c. And I will also create a Toralize.h, like this. And I will begin by putting a small header. So Toralizer.c, and I will include stdio, create a main, and this time I will type out the longer signature for this main function. That is the argument counter and the actual argument pointer, like this, because I'm not going to be using that in the final version, but the client that we're going to code today, that will be it will be used like this. So if we run it by doing ./Toralize, we're gonna enter an IP address like 1234 and a port. So this tool will connect to a predefined proxy server. We're gonna put that in our H file. Let's do it right away. Toralize.h, and let's put the include in here instead. And in this file we're gonna include our local file. So when the file is in your directory, you use quotes around it, like this. And I save this file. Now, if we go into the Sociopath window, we can see in this status bar down here at the bottom, Toralizer.c has changed, successfully updated to server. And if we go into our terminal and go into the directory and check the contents of this file, we see that it has updated. The .h is not here yet because I haven't saved it. It uploads on save. So let's do that. And with regard to the proxy server, I will be using the default values for the Tor package, and that will be using the IP address of 127.0.0.1. That's the IP address of localhost. And let's call this proxy. And I will also make a constant definition for the proxy port, which is 9050 as a default setting. Save. And just to verify, now we should have both of these files here. Right. So both the C file and the H file. Great. So let's just create the most basic things first. I will create a char pointer for the host name. That is the host name that we want to connect to at the end, so to speak, the server that we want to connect to. And we also need to have the port number. Let's just do an int for that. Yes. Okay, so first I will just check that argc, if that is less than 3, which means that we don't have 2 arguments specified on the command line. Then I want to print to a file descriptor which is called standard error, which is used for error messages. It's like printing to the screen, basically. And then we want to do like this, usage host port, like that. And as an argument, we're gonna give argv0. So argv0, if we on the command line specify ./toralize1234 port 80, then this is argv0, this is argv1, and this is argv2. And this is an error, so we'll return -1. And if we have our arguments, we will point the host towards argv1, and we're gonna set the port to, and we can't just do it like this, because the port is an int and this is a string. So we need to use a function which converts a number in a string format to a regular number, a to I. Let me just check if that requires an include file, and we do that by doing man 3 a to I. And we need stdlib.h, which I will put in our header file. Include stdlib.h, and I will also put in string.h and uni.std.h. These are the 4 that I always put in every C program that I do. Let's line up this a little bit better, like this. Okay, So how will this work? We need to figure out how the proxy protocol SOX version 4, how does it work? So let's go to Google. And if we want to have the technical specification of a network protocol, we do like this. We search for the protocol name, SOX4 in this case, and we add RFC. That stands for Request for Comment and is the standard way of describing an official protocol. So that way you will always get the right one. And I'll take the first one here and increase the font size a little bit. This is not a huge file. Some of these RFCs are very big, but it is quite a simple protocol. So there's a two-step process. First, you make a TCP connection towards the proxy server, like any other server, like exactly as you did in my web server video and in the TCP client video. Then when we are connected, we need to create a network packet which looks like this. So from left to right, there is a 1 byte field that is 8 bits for the VN number. And as we can read here, that's a SOX protocol version number, and it should be 4. Then we have something called CD, and CD is the SOX command. It's the code for the command, and should be 1 for connect. So there are two different types of operations that you can do through SOX4. It's a connect operation and a bind operation. So basically a connect operation is when you connect outwards, and a bind is when you prepare for an inbound connection towards you. We are going to do a connect, so we will put a 1 in that field. Then we put the destination port number, and we need to format that port number in network byte order, which is basically that we switch, we cut up the 16 bytes in 2 parts, and we swap them. And same with this destination IP, but this is a 4 byte field, so 32 bits, regular int size, and that's where we put the IP address of the remote server that we want to connect to. And then we need to put a user ID, and I will just put Toralizer there, doesn't matter. And then we need to end that string with 0 byte as usual. And that's basically it. We send that packet, we get a reply, which looks like this, and the only interesting field is this CD field. If that is 90, then the connection has been established, and then you can just send whatever you want. If we get another number than 90, then something went wrong, and we need to deal with that. And then we will send some data just to see that it works. So that is what we need to do. Okay, so I will do like this. I will copy this, and inside our header file I will create a comment block and paste in this one. I want the last line as well, so I see the number of bytes. I think I need to change the size here. Okay, this way we see enough. But in order to be able to create a structure that corresponds to this design, we need to be able to create fields that has the 8-bit size, the 16-bit size, and the 32-bit size. So let's start there. We will use the typedef command to create our own variable types, which will be called int8, int16, and so on. So if we begin with the int8, that's basically an unsigned char in C. That's 8-bit size. So we'll type typedef unsigned char and then our name for it, int8. Then we need the 16-bit size, and that is an unsigned short int. We'll call it int16. And then we need a regular 32-bit int. So that's an unsigned int. And we'll call it int32. Okay, so now we have the different parts that we need. Now we're going to create the actual structure for this packet. So we'll create a struct, which I will call proxy request. And the first is vn, so int8 vn. And the next is cd, which is also an 8-bit. Then we have the destination port, which is 16. Is port. And then we have a 32-bit destination IP field. And then we have the user ID, which has a variable size, but I'm gonna create a username of 7 characters, because that way we can have a 64-bit variable here, which ends in a 0 byte. So that's why 7 and not 8. So basically I will do unsigned jar user ID 8. And this is all we need for the first structure. Let's create the other one at the same time. This one is a little bit smaller, so struct proxy response, and we're not going to be using all these fields. So if we look at this one, the VN is always 0. And the CD will have the code. So the CD is the only interesting field here, because the remaining fields are ignored. So destination port and destination IP are ignored. But we still need to have them defined because we need to have the right size of this packet. So I will do it like this. I will start by creating an 8-bit integer for the VN and an 8-bit CD. Then I will just do int 16 and an underscore character, and then int 32 and 2 underscore characters. We could name these according to this, but I think this clearly shows that they are not important. Okay, so now we have our two structures. We can remove those comments. And make this a little bit bigger again. And I want to create a type def for these structures, so we don't have to type the whole proxy request every time. And I will just call this rec with a big R. And same here, type def struct proxy response, and this will be res with a big R. Okay, so now we have prepared everything we need basically in this file. And we do need a couple of includes though, because we are going to use the following functions. We will have a socket to initialize the socket. We're gonna have connect, and we also need close, age_s, and inet address. So remember what I told you about the network byte order. So if we have a port number, for example, like something like this in binary, so this is a 32-bit, no, sorry, 48. This is a byte. So if we do like this, let's say this is a port number, and I don't know exactly what it corresponds to, but let's say for instance that it's 9050, because it's a 16-bit field, so it looks something like this. Then we need to copy this right part and put it to the left. That is network byte order, that we have the most important bits first. And that is what these two functions are for. age_s does it for the port number, and the inet address takes a string and creates a big. So basically it first takes this IP address and translates it to a big number, and then it makes this network byte order. So these are the functions we need. Perhaps I have forgotten any other ones, but that will be clear when we get to that point. So let's find out what include files we need. Let's begin by socket. We do man to socket and y2 because this is a system call. That's what. How do you know if it's a system call or a library call? Try a library call first, a 3. If you don't get a hit, or if you get a hit that doesn't seem right, try the 2. Okay, so we need syssocket.h. I'll just copy it right on. This, and then we need the connect. That's also a system call. So man to connect, and that's the same. We don't need it again. And what else did we need? Close. I think that's UniSTD that we already have, but let's see. So the close, that is also a system call, and we use it to close down the connection. Can also be used to close down a file. Yeah, UniSTD, we had that already. And then we need the hton_s and inet address. So man, this is a 3, so hton_s. This one. And finally, inet address. Also a library call. So 3. Here we need a couple of include syssocket we do have already. ARPA inet we do also have, but not net inet. Okay, so let's see if this compiles. Since we are using a couple of files, I think I'm gonna create a make file as well. So I will create a new file and I will name it makefile with a big M. And then I will just put in all gcc Toralizer.c -o Toralize. We're gonna be adding a lot of stuff here later on, but for now this ought to do it. So let's save. And when we have a make file like this, then we don't need to issue the gcc command every time. We can just do make, and then it will try to compile. Okay, typo. So let's go into the Toralizer.c, and this should be an if, not an int. Let's save, and we'll run make again. This time it compiled our tool. Okay, so the next step is connecting to the proxy server, because we're not gonna create a TCP connection directly to this host and port that we specify on the command line, we are going to connect towards the proxy IP address from the H file and the proxy port 9050. So that we have done before, creating a TCP client. It's exactly the same as before, so I'm gonna make it quite fast. If you need to learn how to do that, you can watch either my TCP client episode or my creating your own web server series. I will explain by haste though. Okay, so we need a couple of variables. First of all, we need an int, which is called s, for the socket file descriptor return value. We also need a structure, which is called sock address in, and I'll call this sock. That's where we specify all the IP addresses and stuff. Okay, so let's start by creating our socket. So s equals socket, and this is pretty standardized. We always put in sock inet, and second argument is sock stream for a TCP connection, and then a 0 for the third argument. And if this s is less than 0, then I will use the p-error command to easily print an error, and we will specify which function that produced that error. And then I will just return -1. When we create the final version of this, I'm going to use more accurate error codes, but for now we'll just do -1 for everything. Then we will prepare our structure, and that's 3 things we need to add in order to make a TCP connection. First of all, we need to put the SYN family to AF inet. We need to put in the SYN port and use the HTON S, so we get it in network byte order. And then we will just put in our port variable here. And finally we will put in our sock SYN address S address, and that will be equal to inet address and our, no, not our port, it should be our proxy port, and it should be our proxy IP address, nothing else. Okay, so these are the 3 things. Now we need to initialize the actual connection with the connect command. So we do connect, and we reference the socket. The second argument is our structure, and we need to create an explicit typecasting, because we need to change it to sock address struct, a pointer to a sock address struct, and we also need to send the reference. So let's put an ampersand there and the sock, and then we need a size, and I will just do size of sock. That ought to do it. Okay, so this line will connect to the server, but I will also need to do an if statement so we see if it succeeded. And this should return a 0 if it works. If we wouldn't remember that, we can go into the command line and do man to connect and go towards the bottom, and here we will find a section for the return values. If the connection or binding succeeds, 0 is returned, otherwise -1. So I will just do a simple if statement. There's no need to save this to a variable. So if this is not 0, something went wrong. And then we do p error. Connect. And return -1. Otherwise, we are connected to the proxy server. So I will just echo that to the screen so we know what's happening. Then I will close the connection because I want to see if it works. So close S. Return 0. Okay, let's see if we did something wrong. Make it compile on the first run. That's not every time. And let's run it and see what happens. Right, we need to put something here. We're not going to be using that information at the moment. Connected to proxy. Great, so it works. So now we have successfully created our TCP connection towards the proxy server, and the next step is to create the proxy request packet according to this structure that we created before. We haven't created any function declarations, so let's do that as well. So we have a main function, takes in an int and an argv pointer, and when I create those signatures, shard, of course. So if we look at our regular main function, we use this format right here. So a char array of pointers. But when I create the type signature, I usually use this format. Doesn't really matter. Okay, so that's the only function that we have this far. Our other function is going to return a pointer to a request. And let's name this function request. And as arguments, we're going to take in a char pointer, which is our destination IP, and just a regular int for the destination port. And let's make both of these const as well. The const keyword means that we cannot change these variables inside of the function. So it's just input values. So this is the signature. I'll copy this and then I will strip it down so it looks like our main one, because we don't need to have the names of the variables when we do a function declaration. And why do we do these function declarations? Do we have to? No, we don't have to. But imagine that we put our main function in our C file at the top. If we then try to reference the request function, it's not going to find it because it hasn't been defined yet. But if we put our request function on top of the function declarations, then it will work. So that's one reason. But I think a more important reason is so you can have like a better look. You can just watch the .h file and you see the entire structure in a very good way. So always do this if you have multiple files or a big .c file. Okay, that was a small parenthesis. Sorry, I copied over this one. There we go. And then we go into here and we will create this request. So what do we need in order to do that? Well, we need to allocate the memory for this request structure that we're gonna return, and we are gonna reference the length of the structure a lot of times. So I'm gonna create an alias for that, or a macro, and you do that using the define, and then you give it a name. I will call this rec size. And what is rec size? It is the size of struct proxy request. And let's create one for the other one as well then. Define res size, response size, and that is size of struct proxy response. In that way we don't have to manually type out this as soon as we need to reference the size of the structure. And now semicolon at the end. Oh, I misspelled. There we go. Okay, so back to the .c file again. And I'm gonna create a request pointer. I'll just call it rec. Sorry. And I'm gonna start by allocating the memory for this structure. So request equals malloc rec size, like this. And now we're gonna fill this structure with the correct data. So let's bring up the RFC again. So the first thing is the VN, and the VN should be 4. So rec VN equals 4. And if you're not familiar with this arrow, that's basically the same as the dot format. But when you're using a pointer to a structure, you use this arrow to indicate that we need to grab into the reference in order to get the value, or set the value in this case. Okay, so Vn is 4. Then we have the CD, and it should be 1 because we're making a connect request. So rec CD equals 1. Then we have the destination port, and we need to put it in the correct format. So rec dest port equals, and now we use this HTON-S function that I talked about before to switch it to network byte order, and it is the destination port. Then we take the destination IP, so rec destination IP equals inet address destination IP. And then we need to have a null terminated string with our variable, and I want it to be 8 characters. So let's create a definition for that. Find username Toralize, because we need to remove this E. So 1, 2, 3, 4, 5, 6, 7, and then a 0 byte at the end. So I will use string copy to copy into the rec username the username, and the maximum size is 7, and then it will add the 0 byte. Let's do 8. Okay, so now we have prepared this structure. And now we will simply return it like so. And now it will be very easy to handle this, because we have a function which just creates the entire data that we want to send, and we know the size of this structure, so we can just use the right system call in order to send it. Okay, so now that we have our function which creates the packet that initializes the proxy connection, now we're going to use it. So let's go into our main function and let's create a pointer of our structure request type, so we can use it when we want to send the data. And instead of just closing the connection like we have done here, we're gonna set our request variable and use our function. And our request function takes two arguments. It is the destination IP and destination port. And we do already have variables for that. It's the host and port variables. So we'll just use them. So host and port, like this. So now the rec variable is pointing to our packet, and we just need to send it using the right system call. The first argument is our socket file descriptor, which we named S. The second argument is the buffer, and I think we only need to do rec. Perhaps we need to do, yeah, we probably need to do a type definition, typecast I mean, but let's put it like this to begin with and watch the warnings and errors when we compile it. That's usually the best workflow. And we need the size of the packet, and since we know that we always want to use a 8-byte an 8-byte buffer for the username, we have a constant size of our request packet. So we will just use that definition that we put in here somewhere. It is, I think we created a macro. Yes, rec size, that's the one. That is the size in bytes for how big this packet is. So now we send that packet, and the next step in the process, if we look at our RFC, it is accepting this structure back. So we can look inside of the CD property and look for the 90 code. So how do we receive this one? Well, we did use write in order to send the data, and we will use read to receive the data. And for that we need a buffer. So I think the easiest way will be to just create a variable on the stack for that. So buff, and then we'll put the response size as the number of bytes. And before I use read, I always want to make sure that the buffer is empty. So I will memset the buffer with zeros and use the res size, number of zeros. So now we have a clean buffer that we can read data into. Yes, so let's do read, and the first argument is the socket file descriptor, second argument is the buffer, and the third is the size, like this. And if this read operation returns something less than 1, because the number of bytes should be returned, then we know the operation has failed, and we need to show an error. Sorry, I'm a little bit used to the JavaScript strings. There we go. And let's free the buffer. No, not the buffer. Free the request packet, so we don't have things lying around on the heap. And let's close down the socket file descriptor and return -1 for now. So this is if the read operation fails. If it has succeeded, we should have a packet that looks like this in our buffer, but we can't easily access the values inside of it if we only have a string pointer. So we need to create another pointer of the correct type, which is our structure for the proxy response. So we will create a res as well as the rec. And we should just be able to point this towards the buffer. And that's what we'll do. So res equals buffer. I think this should be enough. And now we should be able to grab this value, the CD value. And I like doing it like this. I will create an int, which I will call success. And this will be a Boolean variable. But as you know, we use ints as Booleans. We can use char and other types as well, but usually it's int. And this will be used as a predicate. I'm not sure if you are familiar with the term, but a predicate is basically a function or an operation that returns true or false. And this is American English. I think in the British world they use the word property for this. But since we already use the property term when we describe other things, I think the predicate is a better term. Anyhow, then we can do something like this. So we set success equal, and we go into the structure and we check for this CD value. And I will put this in parentheses, and we do like this. So what does this mean? This means that if the CD is equal to 90, then success will be equal to true. If it's not 90, success will be false. Which means we can do like this to to see if it has worked or not. And then I want to print out an error message of my own. So I use the fprintf to the standard error way. And I want to say something like unable to traverse the proxy error code, and then the error code. I need to divide this a little bit. I'm not sure you know it, but if you have a large string, you can always divide it by smaller strings and put them on different lines. Make sure to encapsulate them in quotes on both instances. And then we will show the res.c, the res2cd value, like this. And we can also do, let's close the S and let's free the rec and return -1. And unless this if clause happens, we have successfully traversed the proxy. So let's inform that with a printf, at least for now. Perhaps we will remove these messages when we are done. Okay, so successfully connected through the proxy to and we will have a %s colon %d, and then I will use host and port like this. And now I will close down the connection. When we finish this program off, we will not be closing down the connection. But since we are only checking right now if it works, if we are able to connect through the proxy, we can close down everything and terminate when we are done. So this code will be removed in the final version. And we will free the rec and return 0, like this. The indentation seems to be a little bit off. Well, we'll see if we get an error. Okay, so let's compile this and see what happens. Okay. And when we are troubleshooting code, especially when we have coded quite a lot of lines of code since we last compiled, always look at the first error, because sometimes if you fix the first error, all the other errors goes away. So don't get discouraged when you see a full screen of error messages like this. Just focus on the one at the top. So what does it say? Rec has no member named username. Interesting. So let's go into our H file and see what we've got. User ID. Okay. Yes, of course. So where was that? That's probably inside our request function, right? Yes, here it is. So user ID, like this, okay. And before I run make again, I press enter a couple of times, so we get a barrier. That way it is much easier to see where the last couple of error messages stops and the new batch starts. Okay, so assignment to res star from incompatible pointer type. Res equals buff. Okay, that's the one I was a little bit unsure about, remember? And I said, let's compile this and see what it says. Because in some of these cases, the C compiler will perform an implicit typecast in this case and work it out anyway, but not this time. So okay, so res is a struct pointer and buff is a string pointer. So what if we were to just do res like this? Let's try that first. Seems like it worked. Okay. So close S, data definition has no type or storage class. That's an interesting error message. Data definition has no type or storage class. Close S. Int close, int fd, uni std. Do we have all our include files? I have never seen that error message before. Uni std, yes. Didn't I call that variable s? Yes, and that's an int. Int. It was only a warning, but a very weird warning. Perhaps something else is wrong in its proximity. If success, fprintf, and the parentheses, then we have the string, and then the end parentheses, close s. What line did it complain about? 94. Okay, it's not this one. It's complaining about this one. Well, there is. Okay. So, let's see. If success, and then we have this, close S, close rec. Yeah, this shouldn't be here. Okay. Let's do this again. Okay, it's compiled. Let's see if it works. So what shall we connect to? I will just do one of my web browsers, and you might have noticed that we didn't put any DNS related stuff in this one. So I can't just put in www.networktechnology.org or something like that. That's something that you probably can add by yourself. See that as an extra task. But for a proof of concept, it's not really necessary. Okay, so I will take the IP address of my web server and let's run Toralize against that on port 80. And if this works, we should see a message that we have successfully connected to the proxy, and we should also see a message that we have successfully connected to the end host through the proxy. Connected to proxy, successfully connected through the proxy to blah 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 blah. Okay, very nice. So this has accessed the web server through the Tor network. And let's add some functionality so it can send some data and read some data, so we can see that it can communicate with the end host as well. That is also stuff that will be removed in the end result. So let's create another buffer. Let's call this temp, and let's do 512. Since it's only temporary, I will not think much of it. So here we are successfully connected, and now I want to send something. So since I'm connecting to a web server, I can use the head command just to grab the information about the web server versions and stuff like that. That's quite easy to do. So I'm going to use the smprintf in order to create the buffer. But first I want to use the memset in order to zero the entire buffer. So, no, not buff. I need to remember I call it temp. And 0, and the number is 512. And then I will do smprintf, and we are gonna put the result into the string variable, the buffer, that we call temp. And we won't be writing more than 511 characters. And what do we want to put there? So let's do head HTTP like this, and we'll end by RN. And on the next line, I will put in host network technology.org. And if you wonder what this RN is, sorry, that is the Windows standard for new lines. So this R thing is a carriage return, which jumps down and goes to the left, or it goes all the way to the left. And the N is, as usual, the line feed. Okay, so now the buffer contains this data. And then we will just simply send it. So write s temp, and I'll do the string length of temp like this. And then I want to zero out the buffer again, or not the buffer, the temp. And then we want to read the results. So we read from S into temp, and no more than 511 bytes. And then we'll just print that to the screen with a regular print S like this. Let's put it in single quotes as well, so we see if there's something weird going on. That's a good tip, by the way. Like if there's a line feed before the data or something like that, then we will see it like this. So this will be on one line and this will be on the next line. Okay, save, and now we will compile, and let's run it again. And this is the response from the web server. As you can see, it works. We are able to communicate through the Tor network, and if I connect to my web server, we should be able to check the logs and see what IP address the requests came from. Var log Apache. Here we are. And let's do tail -3 access.log. Okay, so here is our head, and if we grab this IP address, we see that it's some kind of German address. And we can also do, if we restart the Tor server, so we do etc init Tor restart as root, restart like this, then we issue the same command again. We did get the output like before, and if I check the logs once again, we get another IP address this time. And if we do a host on that IP address, we see that this time it's in the Netherlands. So our program works fine this far. But at the moment, it's just a proxy server client. It's not doing what we intended it to do from the beginning. You remember, I want to be able to do something like Toralize and then run any command like curl against some IP address, and then I want to intercept the connection. I want to run this command as is, but I want to intercept the connection that the actual program does and run my code instead. So it tunnels through the Tor network any program that we want to run. So we can do Toralize and put anything here. We could do like, if we have Firefox installed in the same directory, we could start Firefox with Toralize, and then it will be tunneling through the Tor network. And we could do Telnet or SSH. That is what I want to do. And that is the next step in this process. It seems really advanced, but you will see that it's quite a bit easier than one might think. So what have we learned today? Today you have learned how to create a SOX version 4 client and use it in order to connect to the Tor network. And next time you're gonna learn how to create this nifty little tool that I call Toralize. If you like this episode and want to see the continuation or other stuff in this channel, please subscribe to this channel and hit the like button if you think I deserve it. And thanks for watching, and thanks for today. Okay guys, welcome back. Last week we began creating this Toralize tool, which tunnels any Linux application through the Tor network. We wrote the first part of it, which is a SOX version 4 client. So this is what we have this far. We can supply the destination host and port. So let's take my web server as an example. So we run Toralize, and let's do this IP with a port of 80. And we connect to the proxy. Maybe it's okay, there we go. Sometimes when you use the Tor network, it's quite slow, but more often than not it's quite fast. But as you can see, we connected to the proxy. We successfully connected through the proxy to the destination, and we communicated with the web server on the other end. So the biggest part is done. What we need to do now is the following. We need to turn the client to a library. So instead of using it as an application, we want to have it as a library, and that is a shared library, to be specific, .so files. When we have done that, we're gonna turn main into our own connect, replace regular connect, and we're also gonna save a reference to the original connect so that we can use it ourselves, because our current tool is using connect. If we look right here, so we connect to the proxy server using that system call, and that's why we need to save a reference to it so we can use it ourselves. We also need to grab the IP and port from original connect. So we will take care of the arguments that the application sends to its connect, and we need to take the IP and port from there instead of reading it from the command line arguments like we do now, and then we can proceed by doing what we do now. And then we will just leave it to the original application to take care of the rest of the communication. So we do our thing, and then we exit our function and let the program take over. Okay, so how does this technique work? Well, when you compile your code, you have two options. You can compile it statically, so it's statically linked, and that means that if you use any library calls, or system calls too for that matter, like printf or anything, that code, the printf code, will be saved in your program's executable file. But that's not very optimized, because if every tool on the whole drive would be statically linked, then there will be a lot of duplications, because almost every application uses some form of library calls or system calls. So that's why we have the shared libraries. So instead of, and that's what's usually in use. So we have like a database with a lot of, with a printf code and with a scanf code, and even wrappers for system calls like connect. And when an end application needs to use any of that code, it will collect it from the central repository on the disk. So that's how it works. The thing is, there is a kind of prioritization order, so which we can influence. So if there are two functions with the same name, which one that's gonna execute is decided by a list, basically, and a prioritization order. So if we name our own function connect, and we have compiled this as a shared library, then we can make any application use our code as housekeeping priority 1. And in that way we can intercept and hijack the library call and system call, because all system calls have wrappers in the libraries. Okay, this will probably be a little more clear when we have written the actual code, tested it. And this is not my own invention, this technique. I am following a website, let me just find it, C shared library function hook. Here it is, at R. Jordan-Ace. So it's pretty simple actually. So put s is a function which basically works like printf, but not as advanced. It prints a single string on the screen. So that's the one that he uses in his example. So as you can see, he creates a function with the same name and same signature. He creates a function pointer also with the same signature, and that is for saving the original put s in this case. And then he gets the reference from this DLSym function. So basically you give the RTLD next and the name of the function, and it gives back the memory address where that function is originally located in memory. And then he just does like this. So he checks if you send the argument hello world, and in that case he hijacks the original put s call and changes the message. In other case he just runs the original put s with the same arguments. So this is basically what we're going to do. We're not going to have a condition because we are always going to hijack the original one. We are, however, going to use the original connect function to make our connection to the proxy server. And then we compile it as a shared library. So there's a couple of additional switches we use. And then we get a .so file. And then we basically tell the system to use our library instead by this ld preload environment variable. So we're going to create a small bash script in our case, 3 lines big, and that's what we're going to name Toralize. And then we're gonna use that to set the environment variable and run the command. And yeah, that should basically be it. So let's begin. Let's start by grabbing the signature. So we do man to connect and just copy this exactly as it is, and then we go up to our main and we just paste it right here. Like so. and sockFD address.t, and we remove this, and so we basically turn our main function into this connect function. Like so, and we create a function pointer. And if you have watched my episode about function pointers, you know that that is done like this. I will paste the signature for this original function once again, and instead of connect I will just name this P for pointer. I'll put it inside parentheses and add the star, and then we remove this part, so it should be basically like a signature function declaration. And we use this to point to this DL_sims function. And let me just see where it's located. So man3 DL_sims, and if we don't find it in page 3, we do page 2. DL_sim, perhaps it's without the S, yeah. Okay, so it's inside of this DL_fcn.h. So let's add that to our list of includes, and let's see if he included anything else, only the string. So, and I need to grab the first argument, rtld_next. And you might ask why I don't copy paste, and I try to avoid that when possible, because if I type this a couple of times I will probably remember it. rtld next, and the name of the function is connect, like this. And we initialize the socket, but we don't really, or let's do it like this, by the way. The curl application, or whichever we use, have already initialized their socket, but I think it will be easier just to pipe those two sockets together. Okay, so let me update the signature here as well, so I don't forget that, by the way. Because we don't have any main anymore. We just have int connect. It's int, right? Yes. Did I do int here? Yes. Okay, so int connect, int construct sock address star, socklen_t. So we don't have a main anymore, because that's only for applications, and this is not an application. This is just a couple of functions which are free. Okay, so the application runs connect, and we don't need any of this, and we save this, we initialize our socket, and here we make the connection to the proxy server. Nothing will change about that, but we're not gonna call connect because we would be calling ourselves. We will be calling this P, the function pointer, like so, connected to proxy. And we also need to change our request function. Instead of sending host and port like we did before, let me remove that. So we have int s and we don't have this host. Instead, we need to grab the IP and the port from the arguments. So this is what the application provides. We have the socket file descriptor, we have the length of this structure, and we have the actual structure. So I think the easiest way would be to, I don't want to name this address. Let's call it soc2 and s2 instead. So s and soc, that's ours, and s2 and soc2 are the provided by the application. So we need to look inside of this and get the data that we need. So let's pass the whole structure of that instead as host and port. So we'll just do soc2 right here, and we need to change the signature for our request function, and that is of type struct soc address in and star, struct soc address in star. And I think we need to do a typecast and send the reference. So where were we? Right here. So struct soc address, struct soc address in soc2. I think we need to do it like this. If we get a warning or error, we will change it, but it should be alright. Struct soc address in soc2. So we send that whole structure to this function, and we need to change this as well. So that will be struct soc address in, let's call it soc. No, let's call it soc2, so we know what's what. Okay, so the destination port, we don't need to do htone s and inet address because it's already in the network byte order. So the only thing we need to do is reference soc2 syn port, and for the destination IP, soc2 syn SYN address, source address, like so. Perhaps we need to do some typecasting, but I don't think so in this case. Okay, so now we have the correct packet, and then we save that, then we send that packet. Unable to traverse the proxy. We can keep this for now. Successfully connected through, and this we will not have though. So as soon as we are connected, we are basically done. We don't want to close the socket. We do, however, want to pipe our socket with the end applications socket. So what does it mean, piping? Well, we need to do so everything that's being sent to S will also be sent to S2, and everything that's being sent to S2 is being sent to S, and same with the receives. So we basically become the man in the middle. And there is a good system call which is called dupe2, which does exactly that. So it creates a new file descriptor, and it will be the same value as the second argument, which means that this will be pretty seamless if we give S2. So dupe to S2, and then we return. Did we forget anything? I think we did most of it. Let's copy the compilation flags from this one. So we'll go into our make file, and it will be Toralizer.so fpic shared LDL. Okay, and I will begin by removing the Toralizer binary executable because that won't be necessary. Okay, let's see what it says if we try to compile this one. Okay, dlsims, it should be dlsim. Right here. And I enter down a little bit and run make again, and host undeclared. Okay, that's the message. I don't think we actually need that one. Where is it? Unable to traverse the proxy. Successfully connected through the proxy. Let's just say through the proxy. Enter. Otherwise we need to convert between network byte order and stuff like that. Perhaps we can change this later on instead, if we want to. Okay, it compiled. So how are we going to test this? We haven't really created our bash script. We can do that now, by the way. Let's begin by checking what directory we're in and the name of this. So I'll just do a copy paste of this directory, and I will add this SO file to it. So this is the whole path to our library. And I will log in as the root user. I will go to user bin, and I will open up Toralizer. And this will be a bash file. So we need to have this interpreter at the top, or the hashbang. Okay, so let's export LD preload to this one, and then we want to run the commands, because we're going to run this as Toralizer and then curl or whatever. So we need to send everything that's on the right of this Toralizer. And there is a way to access all the arguments at the same time, and I think it is done like this. Okay, so first we export the LD preload and point it towards our shared library. Then we do the $, and I think it's the @ which will run all the arguments to this script. And finally we unset the LD preload like this. It's probably not necessary to unset it because it's the end of the script, but I think it looks a little better. Alright, so we save this and give it running permissions. Toralizer, and then we test it out and hope that it works. So network technology.org. We will try to do Toralizer, curl, and an HTTP request against this IP address. Connected to proxy. Couldn't connect to server. Let's try restarting the Tor. Perhaps it's a bad connection. That happens sometimes. So Tor restart. Okay. And then we try it again. Okay. Connected to proxy. This time it didn't even give an error message. Let's see what this error code 91 is. If we go back to the RFC, so RFC SOX4. And we go down here. Request rejected or failed. I will try once again to restart the service. Perhaps we are unlucky with the connection. So let's do like this. And then we run Toralize again. At least it's able to intercept the connect function, as we can see by this connected to proxy. But it doesn't really succeed in connecting. Let's just see that this one is up and running. Yes, and it's listening on port 80, right? Let's do just like this. Okay, I don't have telnet here. Let's run it from this instead. So end of telnet this port 80. Okay, it's the server that's not responding. That's weird. Host. Let's try something else. Let's do, I think we should be able to do a regular host name. This is a Swedish site that shows the IP. If we do make this work though, that's not going through the Tor network, the actual DNS request. So the DNS request probably goes outside of the Tor network, and then the actual IP connection goes through. So couldn't connect to server. Weird. Does anything work? Google.sc. Yeah, there's nothing wrong with the routing. But we need to try something else. What if we do a host on this site and we Toralize a curl HTTP and this IP instead? Are we able to connect directly to this one? Okay, that works. Let's look through the code. Perhaps we did miss something. So what happens right here? We set this to the regular connect function. We initialize a new socket and we connect to the proxy with a proxy port using this the regular connect function, and we manage to get connected to the proxy. Everything is fine this far. Perhaps there's some problem with when we grab the IP address. So rec equals request struct sock address in. Perhaps we should not send the reference. What if we were to do like this instead? cd code and Toralize, and we need to run make and then we do host ip.sc, and we do Toralize curl http and this IP. Okay, so now it works, and we should be able to see the IP here, I think, somewhere. Okay, it seems that we go through some kind of middle server. It probably only works against Swedish IP addresses, and we probably don't come from a Swedish IP through the Tor network. We need to try something else. What if we were to do... First, we can test regular first. So if we do host what is my IP.com, we do a regular curl, and we get an error code. Okay, we need to send the host name, and I don't think that'll work, but let's try it again. So curl, or it will work when you do it right here, but I don't think we will get a response. No. Let's just do Google then. So host google.com, and we do Toralize curl http and this IP. Okay, that works. What if we do a host name? Does it even try to resolve that? Yeah, it works. But as I said, be careful by doing that, because only the IP connection will be private, not the DNS request. But as you can see, we are able to traverse the proxy, and we are able to Toralize any command using this tool. So that's the end of this series. I hope you want to subscribe and like if you think it deserves it. And there will be more interesting videos in the future. Thanks for watching, and thanks for today.